Good afternoon, everyone. Let's get started. So we are starting week 9, Tuesday week 9. So we have our last homework 5. Okay, so posted in Canvas. It's due this Thursday. Okay, so when you're done with homework 5, then we'll be done with all 5 homeworks. Okay, so we have finished grading homework 1 to 3. Homework 3 grades should be posted soon. Homework 4 grading is ongoing. We may not be able to, well, probably will not be able to finish grading homework 4 and 5 before the midterm exam. I have talked to our TAs and our graders, so we are going to post a summary of the common mistakes. Okay, so watch out for that. So basically just say, like, what are the common mistakes we have seen in the homeworks, okay? So make sure you check that when it's posted, and if you have questions, of course, come to our office hours or post in Piazza so we can help address any questions regarding those homework questions, okay? So if you have seen, how many of you have looked at the exam, the sample exam from last year, from 2022? Anybody? A few? Was it okay? Not too bad? Okay, hopefully that helps. I know some of you are getting kind of nervous always, right? Exam's not easy, but at least hope that give you a good idea of what kind of questions I'm looking for. Okay, so our plan going forward. Today we're going to finish discussion of cluster analysis. Okay, Thursday we're going to do a review of all the materials we have covered so far, highlighting the ones that I want you to understand, right, and be prepared for the midterm exam. Okay. Next Tuesday, 1 week from today, we are going to go over the questions in the 2022 actual exam. Okay, so make sure you review the materials and work on the questions, right, to see whether you have a good understanding of those concepts. Okay, and then Tuesday we're going to go over those questions. Okay, and then Thursday is the actual exam. Okay, so we posted this survey for the midterm exam scheduling. Okay, I think majority of the students have filled out the survey, but we're still missing some. Okay, so one, if you haven't filled out the survey, okay, and you need special accommodation, please contact our TA. So Julia, our TA, is handling this. So please contact her as soon as possible so that we can figure out what we can do. Okay, so the default, if you're coming to the classroom, taking it in person during the class time, you're good, okay? But any special accommodation, like either you need extra time or like there's a Zoom setup if you need it. So we're trying to figure all that out, and we are actually in the process of confirming, okay, with students who will need special accommodations. So please, if you're in the first category, you're good. Just be prepared to come to the class for Thursday's exam, okay? But if you need anything else, so watch out. If you have filled a survey, okay, our TA should be following up soon to confirm or with any further discussions, okay? So our plan is to have this all finalized soon, okay? Definitely by this week, so we're all ready for next week, okay? Any questions? Yes?
The thing is, in the survey, there was a question about if you can take it online as well, the Zoom, Zoom. So what is actually the form? Even if it's in person or Zoom, what would be the format of the paper?
Right. So by default, if you're in the in-person section, you are expected to take it in person. Okay. If you're in the online section, okay, if you can come to take it in person, we will do that. I think we have enough space in this room. For online students who cannot come to take the exam in person, we are offering Zoom sessions. Okay. So for the Zoom sessions, basically what we need to know, we need you to have your camera on. We need to see you, right? So basically, we need to see you taking the exam. And then when you're done, we need you to send us your answers right after. Okay, so that's the basic setup. So when in the confirmation email, we'll send more instructions. If you are I'm sorry?
Pen paper exam.
Yes, the paper is probably easier. I think most students actually prefer if they do it, like doing paper is fine, okay? But I've had actually students asking whether they can do it on their iPad. Fine too. Like basically, all we need to see is that we're monitoring you taking the exam, and you need to send us the your solutions right after. Okay. Any other questions? Right? If you need like a special accommodation, you haven't heard any confirmation from our TA by Thursday, please reach out. We want to make sure everybody, okay, is scheduled. We know who's taking the exam at what time. Okay. All right. Before I continue, I want to actually quickly switch to another announcement. This is actually about us, our center. So I mentioned at the very beginning that I work on electrical transportation. So we have a center that's called Aspire. So we're actually doing a research expo. Okay. So the focus is on electrical transportation, but I really want to highlight because I'm leading the data research at the center. So we actually see a lot of opportunities for all kinds of data you can utilize, right? Going from the battery system to the vehicles to the charging, individual charging stations. Then you can talk about the power grid. You can talk about the individual people. You can talk about different transportation modes, fleet operators, and also policy making, environmental aspects, social justice. So all those actually are related to the center. So if you're interested in either generally electrical transportation or you're interested in how data can be useful in this kind of setting, please come. It's today, this afternoon in the DLC 1B70 from 4 to 5:30. Okay, so there'll be food, there'll be snacks, there'll be posters, demos. It'll be a good opportunity for you just to learn more about our center. And of course, I'm always happy to talk more. With that, I want to switch over to our class. Okay. All right. So we have been talking about actually in the previous lecture, we finished the last bit of chapter 7. This is about classification, right? Advanced semesters. Okay, so we particularly was finish up the rich data types and other related techniques. Okay, so the high level thing is that when you're working on classification, right, think about what types of data, right? So we talk about like what if you have like graph data, what if you have a sequence data, right? So you may basically using different types of information as you're working with like your classifiers. Okay, other related techniques, we'll talk about multi-class classification, right? When you have binary classifiers, okay. We also talk about interpretability, which is important, right? Because some methods can be very easy to explain. Some methods are more like a black box, okay? So those are all things you need to consider as you're working with the different classifiers, okay? We also briefly talk about reinforcement learning, right? That's also related, right? You can actually use that to learn the information, or like when you have some kind of like evaluative feedback, right? Rather than a ground truth label, okay? We then started talking about class analysis. Okay, so chapter 8 is covering some of the basic ideas and the methods. Okay, so at a high level, right, what do we mean by clusters or cluster analysis? Right, so here it's unsupervised, meaning that you don't have any predefined label or predefined categories. Okay, so you're being just provided with objects. Right? Objects are represented by different attribute values, and you need some way of determining, right, similarity or distance. Okay, so at a high level, classes really just say grouping, right, of objects, meaning that you have certain objects that they are closer to each other, so that means they have a high intra-cluster similarity. Okay, but they're different across clusters, so that means that between clusters, the similarity is much lower. Okay, so how do we find the clusters? Okay, so we started talking about the partition methods. Okay, so by now, like you, hopefully you all know, like the high-level idea with k-means method, right? It's a partitioning method. So high-level idea is that, like, okay, you have a k, you need the k. Somebody need to tell you the parameter, right? How many clusters you want to generate, okay? And when you with k-means, that basically says that, okay, I'm going to assign those data points, right, into those k clusters, okay? But what is that if you want to do this in a brute force way, right? It's very like time-consuming, actually almost infeasible for reasonably large data sets, okay? So we're using these heuristics, right? So with the k-means, we're basically saying that, okay, I'm computing the centroid or the mean, right, of each cluster, okay? And when I'm assigning objects, right, it's kind of natural for me to assign you to the closest centroid. Okay, so that's the high-level idea. Okay, so we talk about like the computation complexity, right? So basically, you have n objects, you have k clusters, and you're running this t like iterations. Okay, so this really big O of nkt. Okay, but then with the k-means, like they also said like, okay, you cannot work with, like, say, if it's numerical data, yes, you can define the mean value, right? But when you cannot define the mean value, then you need something different. Okay, so we then also talk about k-medoid. Okay, so before we ended in the previous class, we started talking about hierarchical methods. Okay, because with the partitional methods, right, the k-means that you need to define k upfront. Right? So like, tell me how many clusters you need, all right? But one benefit with hierarchical methods is that you don't need to specify, right, how many classes up front. Rather, you're just playing with your data sets, right? And you can actually find the clusters at different levels, okay? So the general idea with the hierarchical is that either you're going bottom up or top down, right? So bottom up means that you're kind of like start with the individual data points, you're merging them. Every time you find the two classes that are closest, right, merge them, okay? But if you're going top down, you're dividing, right? So you start with one cluster, right? Every time you try to find some way to split your data sets, right? So you're dividing into smaller and smaller clusters. Okay, so there's one classic method which is called BERT. Okay, so the general idea is actually it's about hierarchical, but also actually using some of the partitioning thing. Okay, so what it's trying to do is that say, okay, I have a lot of data points, right? I need to, of course, find the clusters in a hierarchical way. But since I have too many data points, okay, so the first stage is actually about like a local grouping. Okay, so what they call like micro clustering. So that means you want to roughly put them into kind of those blobs. Okay, because when you're working with the hierarchical thing, like it's actually like you're reducing the number of classes you're working with, right? So you get to a point that okay, somehow those blobs are pretty close to each other. Okay, and now those blobs, okay, or those clusters, right, become what we call microcluster. Or those actually will now become more like a node or a point, like a super node, right, in the second phase. So second phase is like a partitioning, okay? Because now if you're doing partitioning on the individual data points, right, it's very expensive because it's big old NKT, right? So it's the number of objects. But now once you group those objects into clusters, okay, so now you're working with the cluster level. So you're partitioning, you're actually really partitioning those clusters or microclusters, okay? So that's what we're referring to as the macrocluster phase, okay? So it's, of course, you need a way to determine, right, how close you are to a cluster or how when you combine clusters. So it's actually using some very interesting properties. So one is called clustering features, CF, okay? So of course, for any cluster, if you're trying to calculate, right, the CF, the features of that cluster, one, you have this n, that's basically how big the cluster is, right? The second one is LS and SS. So basically, it's the linear sum and the square sum, okay? So one thing you may notice that like this is actually easy to calculate, and also when you have two clusters, when you're trying to combine them, it's also easy to take this and then calculate this, right? You just need to add them up, right? You don't need to redo this for the individual points in those two clusters. Okay, so this turns out to be actually a very efficient approach, and it can quickly give you like some good hierarchical clusters. Another one that's related, but it's actually have a very different approach. Okay. So in the previous approach, we're basically talking about the closeness, right? While here, we're making it more explicit as some kind of graphs, okay? So in a visual way, if you see, like if you take a graphs, right? So generally say if the points are not uniformly distributed, right? So you tend to see denser areas in your graph, okay? And some like sections of your graphs are more spread out, okay? So one way to look at this is what we call this edge cut. Right? So basically, you're cutting off some edges, and now your graph becomes disconnected. Okay? So that's the high-level idea. So you start with your data set, right? And now you're trying to construct what we call a sparse graph. So basically, you're just taking your top k. Okay? So you're constructing edges. Okay? Like with your top k neighbors. Okay? So once you have constructed this graph, right? It's not all the connection, but as this graph should give you some sense about which points are close to each other, right? So then that means they have like edges that are connecting them, right? And there's like a denser connections, okay? While for like clusters that tend to be more like further out, as you can see here, right? For example, if I cut off this edge, I can already like disconnect, right? Or this and this two, I can already separate out this whole like graph, okay? So what do we do, right? We take this graph, we partition this graph, so we have this kind of smaller kind of cliques or this densely connected subgraphs. Those are smaller, like kind of similar to the microclustering approach, right, in the previous method. Okay, so I split it, right? I have those like pieces, okay? Now you're trying to combine them, okay? To the point that you can then find those like bigger like clusters and which are the final results, okay? So if you look at this, right, I construct my sparse graph and then cut it out. So I have those smaller, dense pieces, and then trying to pull them back, like adding them back to the point that, okay, this is still like how to say, the distance or similarity with like within this graph, like the subgraphs are still small. So that is your final clusters. That's how we get to these three clusters. Okay, and of course you need a way to define, right? Because every time you say, okay, whether I cut, right, this like these two subgraphs or not, or whether I combine them, you need a way of measuring, right, the closeness, okay? So typically with the graphs, right, usually you're talking about number of cuts, right? So how many edges you have to cut, but also if you have weights along your cut, right? So if you have a weighted graph, right, then you say not only I'm cutting, say, 2 edges, I'm actually cutting, like, say, those 2 edges, the combined weight is a certain value. So you're trying to find ways to cut along edges, right, fewer edges, and also smaller weights. Make sense? Okay, so if you apply this in, like, for example, like social network, right? So we actually did some experiment, like, so we're trying to find like group dynamics, right? So we're trying to figure out like individual members, right, whether they're interacting with each other, either direct interaction. So that means, okay, I have a friend link. That's one thing. But also you can add a weight. That means, okay, you can have, say, like the interaction frequency, like how often do they post or like or interact with each other. So then actually you have kind of have weight information. So using that, now you're constructing a graph of social ties. So that means like, okay, I'm like loosely connected with this side, I'm more connected with this group, right? So that will again give you a sense about the connectedness, weighted, right, social ties among like a group of people. And that will then allow you to identify those clusters, right? Those are like smaller communities, right, of people who are more closely connected to each other. Okay, so one thing you will see is actually very powerful with this kind of approach is that you can deal with arbitrary shapes. Okay, remember earlier when we talk about like your clusters, right? So depending on your application scenarios and depending on the attribute values and different functions, right? You want to say, okay, whether my clusters are of a particular shape, like it has to be like convex shape or it has to be kind of rectangular or whatever, right? But with a chameleon, the idea is really because you're basically growing, right? So you're cutting those into smaller pieces and then attaching them, right? So there's really no, how to say, constraint or restriction in terms of how those pieces are connected, okay? This is quite different from the k-means method, okay? Remember with the k-means, the heuristic is that you always assign to the nearest centroid, right? Because of that, right, we had this kind of donut shape example. That doesn't work with k-means. K-means cannot work with this kind of like non-convex shapes. Okay, well here you can already see, right? Chameleon actually can generate shapes like very different, like clusters with very different shapes. Okay, and of course that really also depends on like how you're defining some of the parameters, right? For example, like to what extent do you cut, right? To what extent do you combine, okay? But still, it gives you this flexibility so you can actually adapt to very different shapes, okay? All right. Now we'll talk about partitioning methods, right? Partitioning method basically iteratively assigning points to clusters, right? Update your clusters and then repeat, right? While with the hierarchical methods, you're basically trying to identify clusters at different granularities, right? So you can go, like either you can keep splitting or you can combine things, okay? So what we have seen is that that actually hierarchical approach actually can be quite powerful, right, to apply to different like scenarios. Next, we can talk about one more, okay? This category is called density-based methods, okay? So density generally just refers to, like, if you look at, like, if you visualize, right? Basically, in a neighborhood, right, you tend to see denser points. And if there's like some natural separation of the neighborhoods or clusters, then you tend to see like a more sparse areas in between clusters, okay? And that's what we're trying to leverage when we're trying to utilize the density, okay? Now, of course, in this case, you need to, again, figure out what is the density, right? To define density, you define a neighborhood, and then you count how many points you have in that neighborhood, right? So that's the natural notion of density, okay? So to start with is that you want to be able to, okay, identify dense areas, okay? We're going to talk about two methods after this, okay? But because it's a density-oriented, right, it also has this natural property that it can be of arbitrary shape because it's a density-based, so I'm less concerned about the global connectivity. Rather say, oh, this is a neighborhood that's dense. I keep growing. I can grow it in any direction, so I actually can still find arbitrary shapes, okay? Also, it's a density-based, right? So actually, it's really helpful in terms of handling noise because if it's a density, right, you may have a few points that are kind of a little bit like, kind of like further out or whatever, but that usually doesn't change the density of the area significantly, right? So as a result, you're more robust, okay, to this kind of like noisy data, okay? So let's look at some specific approaches. Oh, it's not synchronized. Okay. So this is called a DB scan. Okay. If you search DB scan is actually a widely used method. Okay. Because it has actually very a natural kind of simple notion, right? So what you're looking for is that you're defining this epsilon neighborhood. Okay. So epsilon, of course, is a parameter, right? So you say, okay, within this neighborhood, how many points I need to consider that's a dense neighborhood. Okay. So once you define that, right, so you basically have these two parameters, epsilon, that is the neighborhood size, and then you have a threshold, right, minimal number of points I need to have for this neighborhood to be considered dense, okay? Once you have that, right, so now you see, look at those pictures, right, so you can now grow your neighborhood, right? So you basically say, okay, I can continue, right, connecting my neighborhood as long as I'm in a dense area, because the general idea is that here you're dense, you check the maybe to your left, yes, still dense, so you keep growing, right? So you can basically identify all those connected neighborhoods that are dense, okay? So you keep growing until you get to the edge. Edge means that if you go further, they're no longer dense, okay? So you naturally have this kind of a connected, right? It's kind of more that's why you can actually swerve around different shapes, right? So you start with a P, you keep going, and then you say until you get to the side. But also this is another example showing you how your neighborhood, right, doesn't need to be follow a particular route. As long as they're connected and they're dense, you can build out your neighborhood, okay? All right, so with this, right, so we're basically just looking for so what do we call directly density reachable? So that means I can connect along the way. There's one hop, right? We're both dense, okay? And density reachable, that means it's not one hop. I can do multiple hops, okay? And then you have this density connected. Just say, okay, you may have a few different neighborhoods, but as long as they have some way of connecting to each other, you can combine them into a one cluster, okay? So of course, you can see some of those are really kind of important for you to consider is those parameters. You need to play usually in the real world setting, right? Depending on the kind of data you have and the kind of density function, you want to play with the different parameters, right? Epsilon and the mean points, okay? So you will see that can give you different results, okay? So usually play with it so that you can actually get to a point that the clusters are reasonable, okay? So there are some notions, if you look at the paper, you can get some of the more specific, but the general idea is that you have this core object. That means you're kind of in the middle of a dense neighborhood, right? Versus the border ones, that means you're still kind of part of the neighborhood, but you're kind of already at the edge, Okay, so think about it like residential area or like in the physical space, it could be like I'm just a borderline, I'm connecting this, right? Or if you think about like a research community, like I'm here, right? But I'm connected to people this side, but I really don't have much connection on the other side. Okay, but overall, right, this would allow us to play with different kind of neighborhoods, and also another importance is about this outliers. We'll talk about that about outlier analysis later. So once you have those kind of density or dense neighborhood, it's actually a very natural way for you to then be able to identify outliers, right? Outlier just mean that okay, you don't belong to any kind of dense neighborhood. You're just kind of in an area by yourself, right? So this is actually also very useful, like downstream usage of the density neighborhood definition. All right, so we're talking about how the parameters, right, is something you need to play with. This is just a way to visualize like how different choices of these two key parameters, right, can give you very different results. Okay, so at a high level, right, so we say it's the epsilon and the mean points. So the general thing is that you're defining the density, right, and then defining the neighborhood, okay? So for the same kind of epsilon value, right, the higher threshold, that means you need a denser, right, neighborhood for it to be considered part of the cluster, okay? So you can adjust that differently. So basically that means that you need a really dense one versus a bit of kind of more like a fuzzy approaches. So in this case, you can see, right, so here, actually this one versus this, you can see like that's why sometimes visualizing your results, your cluster results is very helpful, right? Because once you visualize it, then you can see, okay, whether this makes sense to have this to be one neighborhood or you want to have an even finer one. But as you can see in this case, it gets too spread out, okay? Or actually you say, I already know this is one, actually I'm interested in some of the smaller neighborhoods. Fine too, right? So that's about really just a way of showing how you can control this and play with it, okay? So similarly here, right? So if you can, like if you have like at least the lower threshold, then like everybody's considered into one dense neighborhood. They're all connected, right? But then if you kind of refine this, like become more restrictive, then you actually get the smaller components. Okay, so again, which one is more natural for you depends on your application. But this at least allows you to play with the parameters and be able to identify clusters that are more meaningful for your application. Okay, so that's one approach, right? In this case, neighborhood, right? The other approach is quite different, okay? It's still talking about density, but now it's using a statistical kind of modeling process, okay? So instead of trying to just visually, like not visually, computing like individually the neighborhood, right? I'm actually trying to figure out some kind of like density function, okay? Which is really the statistical distribution, okay? So the approach is very good because it has a solid mathematical foundation, and it's really good because you're modeling, right? You're modeling distribution. So they're fairly robust against like data sets with a lot of noise, noisy data, okay? And also, once you're done, you really need only the model itself, right? So the density function can be easily represented, right, by a few parameters. So that's actually also a very good advantage, okay? And we show that it's fairly efficient, okay? But the question, of course, how do you get to those parameters, right? So let's look at the steps, okay? So starting point is what we call inference function. Okay, so that is defined for each data point. Okay, so now you consider in a community or in a physical space, right? Whenever there's some an object, right, at a particular location within space, right? This particular object has some inference in the neighborhood. Okay, so you could, depending on like how you define it, this is like you can have some kind of like Gaussian distribution, right? Meaning that like closer to me, like you're very, like say I have a bigger inference, but if for the outer I don't have much inference, right? So this could be like applicable in the say social community, research community, or in the physical space. If you set up like a control like center, then you can like do something, right? So that is defined for each data point. So that means within my neighborhood, I have some function to like capture the inferences of this particular data point, okay? But now when you have multiple data points, you're basically just adding them up, right? So this is what about what we call overall density. So that basically means that when you put the data points, right, on a particular like a plane or space, right, each of them have their local distribution of the inference function, okay? So for example, if you put a few kind of experts, right, of data mining, like they're next to each other and they're together, so their combined inference function can be really big, right, in that particular local area, okay? So that is the idea, okay? So there's kind of like basically you're summing up, right, the inferences. Okay, they may not always be positive. It could be positive or negative, but when you add them together, right? So the overall impact is what we're looking at. Okay. Similarly, if you're talking about, let's say, you have like a different effect of, say, traffic, right? So then you say, okay, there's like a traffic going this way, traffic going that way, but again, you're looking at the combined effect. Okay, whether it's helping or actually releasing or making like some of the congestion worse because now you have the combined effect, right, from multiple directions. Okay, once you have that, okay, you now actually, you can now then what we call is the density attractors. This is really the clusters we're looking for because it's the combined effect, right? If they're more significant in certain neighborhoods, and those are the clusters we're trying to find. Okay, now let's actually try to visualize this. Okay, so at a high level, as I said, right? So if you look at a particular plane, right, and then you have this kind of like you started by looking at the individual data points, but when you add things up, this is what you see. Okay, so that's the combined effect, right, in the neighborhood. Okay, and of course, depending on the granularity, right, you can see whether this is more like a high like peaks or you have a bit of more of a gradual kind of like effect, right? But ultimately, what we're looking for is this like you pick some kind of threshold, right, and then you can identify whether there are clusters, right, islands or something, right? So in this case, like if you say depending on where you're cutting, right, if you cut this way, you tend to see like groups or classes like that. Or if it's like you have a different threshold, then you will see there'll be kind of like either finer or like coarser granularity. But the high level thing is that you're looking at, so for each like cell or data point, like not data point, each cell here is the combined effect of all the neighboring objects with their inferences, right? And then you're looking at whether the inference is above certain threshold, okay? Or you can look at the overall plane and find the top ones, okay? And that is your cluster, okay? So as you can see, right, DBScan, then DenCrew, so those are two very different approaches, right? But they are both using density, okay? One is about neighborhood-based points, right, in a neighborhood, while the other one is about individual inferences, but it's the combined inferences in the particular like neighborhood area. But in both cases, you're looking at combined density being significant enough, and that is why they naturally form those clusters. Okay, so this is also another example showing how the density-based approaches, they can work with different shapes, right? The classes can be of arbitrary shapes. They're really just looking for areas that are dense, okay? All right, so we talk about partitioning methods, hierarchical methods, density-based methods. The next one is grid-based methods, okay? So that's actually very simple, okay? So with a grid-based, the idea is that instead of trying to like work with the data points, because all the other methods, they basically work, like say, partitioning, you're working with individual data points, right, assign them. Hierarchical or the other ones, you're still looking at individual data points. So grid-based approach, you just say, okay, I want to come in, I just divide up my space, okay? Once I divide up my space, and then within those like subspaces, now I can look for like whether I have sufficient, right, like number of data points, okay? So the general, of course, it is also naturally a hierarchical approach because you don't cut it once, right? So you do cut in a hierarchical way, but you are dividing up space rather than dividing your points, okay? So once you have like your spaces, then you're looking at, right, within this space, like how many data points you have, whether that is by itself is a class or not, okay? So there are two widely used approach. So let's look at the first one, okay? It's very simple, okay? So the STING method, right, is we talk about statistical information grid, okay? So what are we doing, right? So you just iteratively, you divide up the space, okay? So the first one, I do like 2 by 2 cut, right? I have this 4, and each one now continue, do another 2 by 2, another 2 by 2, right? So when you go down like a couple of levels, then you get to the point about each one is a grid cell, okay? Starting point. These have regular shapes, right? So the class you find need to follow those shapes. Okay, this is very different, right, from the other approaches where they actually can have arbitrary shapes. Okay, so grid-based method, they can, right, they use a particular way with this, like partitioning the space. Because of that, okay, they are dependent on the space complexity rather than the number of objects. Okay, so this can be very useful when you have a large number of objects, right? So instead of working on like partitioning individual objects, you basically just say, okay, I just need to focus on the like cutting the space and finding the ones that are like dense enough. So you can probably quickly filter out a lot of those like cells that just do not have enough points or have empty points, right? So you then focus on the ones that have points and enough of them. Okay. So as I said, right, it depends on the big over G. G is really the grid cells at the bottom level. Okay, so this complexity is based on the number of grid cells you work with rather than the number of data points you have. Okay. And because that, right, this is independent, right, meaning that once you split, like divide up the space, right, it's more like a divide and conquer scenario. You can easily parallelize your processing. So that wise it can be very efficient because you can parallelize the computation, right, of the different space like areas. Okay. Also, if it is a hierarchical, so you can work with different granularity, right, to have final crosser granularity. Okay. But because of that, as I said, right, your space cutting is usually horizontal, vertical, so you cannot work with like arbitrary shapes. Now another one, okay, this one's called click. Okay, so it's also trying to work with the space, but it's trying to do this in a little bit more like a maybe smarter way. So meaning that instead of just blindly divide up the space, okay, they actually try to look at the distribution. Okay, so in a way that like what do we call the dimension growth, right? So you grow from the single dimension to high dimension, okay? Now, to do this, right, so you look at it, so if you look at, for example, if I look at an individual dimension, so that's a distribution. So that means you have values or data points, right, like within this range. Okay, so what you do is that you take this range, you divide it up, and then you can look at, right, where you have like some like values or concentrated values, okay? And then you work with another dimension, right? So that's the other one. So naturally, or like similarly, you can like divide along that dimension, but again, focusing on the ranges that actually have some like number of data points. Okay, so this is like it's really a combination of a density base and a grid base because you're looking at areas that are dense enough, right? Because I don't care about like if you look at any dimension, right, or any combination of the dimensions, right, you can already remove or ignore the areas that are not sufficiently dense. Okay, so that's the density part, okay? But it's also grid-based because you're trying to divide up your space, right, based on the different dimensions, okay? So once you're done, you can see what kind of shape we get. Okay, so in this particular case, right? So I have like somehow I figured that like along these two dimensions, I have those like grid cells being like dense enough. Okay, so when you put it together, right, you have something like that. Okay, so this is a shape you could find, right, using this approach. Okay, so ultimately, right, you have those like non-overlapping rectangular units, but then when you combine them, that is your cluster. Okay, so in a way, you can say it can work with, right, different shapes, okay, but it's still kind of bound by this kind of how you split your space. So you still have this kind of like rectangular like edges, right, as your boundary, but because you can work with different granularity and also you're combining different dimensions, you can then find like shapes that are irregular to some extent, right? They're irregular even though the individual like cell boundaries may have to be horizontal or vertical. Okay, so this is a grid base. You're dividing up the space, but also using density because you only focus on the like areas that are dense enough. Okay, so chapter 8, we'll talk about the basic concepts and some of the typically used methods for cluster analysis. Okay, moving forward, chapter 9, we're going to talk about some of the advanced methods. Okay, so what are the things we haven't covered and are still important to consider? Okay, so at a high level, right? So when we talk about cluster analysis. So far, when you talk about clusters, we say you belong to a single cluster, right? Because all those clusters are non-overlapping, meaning that you either belong to this cluster or you don't, okay? But in the real world, there may be scenarios say, okay, I don't know, I want to assign some probability. Instead of 0 or 1, like whether you belong to it or not, I may say there's certain probability, right, for this object to belong to a particular cluster. Okay, and that actually turns out to be very useful in many real-world settings. So we're going to talk a little bit about probabilistic-based methods. Okay, high-dimensional data, that's actually very common in real-world setting. So clustering is particularly challenging when you have larger number of dimensions to work with. Okay, so we'll talk about that a little bit. By clustering, that's another thing we'll talk about. Then clustering graph data, and then semi-supervised clustering. Okay, so starting point. Okay, so this is really like some of the notions started with the fuzzy clusters, right? Because when you talk about cluster membership, right? So either say I belong to it or not, but potentially, right? You may actually have a potential membership in different clusters. Okay, think about the idea of say you have a document, right? So, and then you're trying to decide what this document is talking about, right? Which category, right? Like this document is all about travel. This document is all about football, or some kind of scientific topics, right? But sometimes, right, this document, right, may actually belong to multiple clusters, okay? But with a different weights, okay? So that's really the notion we're trying to capture. Okay, some of you, if you're working with topic modeling, right? If you're talking about some kind of text analysis, or if you're trying to do some of the grouping, right? You may realize that sometimes it's not clear yes or no, right? So we find this need, right, for these fuzzy clusters. Okay, so the notion with the fuzzy clusters is simple, right? Instead of saying that we all belong to it's a 0 or 1. Now you actually have a partial value, right, between 0 and 1, okay? So you could have, right, a partial weight. Of course, the combined weight need to be 1, right? So you have the combined value, right, so that when you add this all up, then it has to belong to one of those, right? Okay? Now the question is, of course, how do we determine that, right? Because earlier we already said that, right, even if we're only doing this 0, 1 single assignment scenario, it's already so hard, right? We have to use a heuristics, right? K-means using this heuristic method determine this 0, 1 membership, okay? If we're trying to play with the probabilities or this different weights, right, that is even harder. Now the complexity is much higher, okay? So to do that, people have come up with what we call some kind of modeling approach, okay? Again, this is statistical approach, right? So the idea is that instead of trying to figure out individually the probability of a data point belonging to one of those clusters, okay, I'm using this underlying assumption that all the data you're seeing, right, is being generated by some kind of underlying models, okay? So each model, right, so usually there are a few models. Each model has some kind of statistical distribution function, okay? And your data point has certain probability being drawn, right, from that, from one of those models, okay? So that's a high-level idea, okay? Why is this useful, right? So this is actually one concrete example, right? So if say this is actually about different, I think these are different cameras, right? So usually the idea is that if you look at the price of a camera, you can probably decide whether this is a consumer line or this is a professional line, okay? But turns out, right, you actually have some kind of overlap, right? It's not clearly, say, giving a particular price is either consumer line or professional line. If you have some price in the middle, they actually could be, right, a higher end model for the consumer line or a lower end model for the professional line, okay? You don't know for sure, right? But if you model individually, right? So basically like this curve, right? This one is a model you're trying to capture for the consumer line, okay? And then you have another model that is helping you to capture the professional line, okay? Now you have these two models together. Now you can actually look at the price values you have and knowing that they have some probability of coming from each of those models. Okay, so with that, right? This is what we call like, we have probabilistic clusters. So that's the probabilistic distribution, right, for each underlying model. And then we'll talk about mixture model. So the idea is that it's not just one model, right, generating your data points, okay? Rather, you're looking at, right, potentially multiple models, okay? So naturally, it's the combination of multiple clusters, and your data may come from each of those clusters with certain probability, okay? All right, how do we do this? Okay, so ultimately what we're trying to do, right? So you have my data set. So this is my D. D is the data set I'm being provided with all the data points and their attribute values, okay? I'm trying to find this C, right? So C is my mixtured model, okay? So what I'm saying is that if my data is being generated by this particular model, right, or mixture model, I have a way to calculate the probability, right? What I need to do is basically I go through each of my data point, right? So if it's generated, like if you say O sub I, so that's a particular object, right? What's the probability of this object being generated by my mixture model here, okay? And by mixture model, that means I will go through my K potential models, right? And each of them have certain probability of generating O sub I. And the combined probability is the likelihood for me to see each of those objects and the likelihood for me to see all the n objects I have in my data set. Okay? So that is what I'm trying to capture, right? So I need a way of representing C, okay? Once I have this mixture model themselves, then I can calculate the probability. And ultimately, we're trying to find a set of a C or this mixture model such that the overall probability is maximized, right? Like what kind of models, like combination of models would give you the highest probability of observing D, okay? That is what we're trying to do. Okay, so we're trying to find C, right? This is a set of C. C would be consist of K probabilistic models, right? Such that the probability of seeing D giving C is maximized. That's what we're trying to do, okay? How do we do it? This actually then leads us to a very, again, very widely, very actually effective approach, which is called the EM method, okay? Expectation maximization, okay? You will see this one is actually very similar to K-means, okay? So just a big refresh, quick refresher of K-means, right? K-means is saying that, okay, for each iteration, I go through my N points, and for each data point, I'm trying to decide, right, which cluster. So I'm checking through the K clusters, finding the closest one and assign to that cluster, okay? The EM method works very similarly, but the difference is that instead of assigning this data point to only one cluster, I'm trying to compute the probability, right, of this data point belonging to each of those K, okay? So that's the main difference, right? Instead of a single membership, I have probability distribution of the membership, okay? Now, I have an idea, right? So with EM method, so they usually like assuming for them some kind of like a distribution. So Gaussian distribution is actually widely used, okay? So if you do this like 2D Gaussian distribution, you basically have your mean point and you have the neighborhood, right? So once you have that, you have a way of computing, right? If I have a mixture model, like a Gaussian model here, what is the likelihood I would see any of those data points? That you can compute, right, mathematically, okay? So assuming, right, that your mixture model is a mixture of K Gaussian distributions, all you need to is find the parameters, right, for your Gaussian distribution, which basically are the two for each of the model, okay? So in our simple illustration here, like giving all these data points here, you can naturally probably find like this is a one, this is a kind of nice Gaussian distribution, and there's another one, so that would give you the cluster, right? But even with that, right, there's some probability, because meaning that even if this is the like a one kind of concentration cluster, but for data points that are further out, they may still have some probability of being generated, right, by a cluster or the model that is further out, which again makes it actually much more powerful to work in the real world setting, because real world, they have a lot of noisy data, right? So you don't have this absolute membership, but you just have like the probability, right? Even though the probability is lower, but it's not like negative, or it's not zero. So you could actually still capture those fuzziness, okay, in your data set. All right, so concretely, okay, so it's called EM method because they have the E step, you have the M step. Okay, so E is the expectation step. That means given the assignment, you're trying to calculate the probability, right? Okay, so assuming, right, you start with some kind of parameters for your, let's say, Gaussian distribution. Okay, with that, you can already calculate, right, the probability, right? So given given your current model, mixture models, right, you can calculate the probability of each object, right, O sub I, coming out from a particular model, okay? And then you can just normalize it, right, across this K, okay? So that's the E step. That means given the current model, what's the likelihood of this object coming from each of those K models, okay? Next step, maximization, right? Because this actually, again, similarly as you're kind of like in the K-means, right, you do the assignment, right? And then you're trying to adapt your centroid, because your centroid will be adjusted when you have the new assignment, okay? So in this case, right, so maximization basically just says, okay, giving, right, the distribution or the probability of those objects coming from each of those models, right? Now I can update my models. Because with the Gaussian, right, we're calculating the mean, we're calculating the sigma, right? So it's the other way, right? The first one is for each data point, you look at each of the models and see, okay, what's the likelihood I'm coming from those models, okay? And now the second step, in the maximization step, for each model, right? Now you look at all the individual data points and say, okay, if you have certain probability belong to me, you have certain probability belong to me, as an aggregated way, what will be the new like parameter, right, for my model? Because if I know you all belong to me, then you say, okay, I now see a lot of people points like pulling me to the other side. So I'm kind of like trying to adjust, right, so that the updated model parameters, right, would be able to capture, right, the new updated membership, weighted membership of the individual data points. Okay, so very similar to K-means, with the key difference being this partial membership or this probabilistic distribution across the K, okay? So same thing, you don't need to memorize it, okay? So if you need to do it, I'll ask you to use the formula, but hopefully you know how to read it, right? You should see here is that I have a way of calculating knowing my model, the current model parameters, I have a way of calculating the probability of each object belonging to each model, okay? And giving that weighted, right, membership, I can then update, right, my parameters just based on which objects belong to my model with what probability, okay? All right, we're going to get into the details. But at a high level, right, so this method is shown to be actually very simple to implement. You can probably easily find the library functions supporting this, okay? Has been shown to be very effective, okay? It's actually very useful in many real-world settings. It's really powerful. It works with a lot of kind of large-scale but noisy data sets, okay? It can be easily calculated with a few parameters, because those statistical models, they only usually have a few, right, parameters you're trying to figure out, okay? It is still because you're still kind of trying to play with the local model, right? So it can converge quickly, but still doesn't guarantee, right, global optimal, because you're still kind of in a way kind of adjusting, right, in your neighborhoods, right? So depending on how you choose your neighborhoods or your initial parameter values, right, you may or may not, you're not guaranteed to find a global optimal. But generally, we have actually seen pretty good performance, okay? And of course, if you have many classes, remember, right, the complexity of your like computation really depends on how many models, because this is a mixture model method, right? So if you have many models that you need to work with, right, that of course would like increase your complexity significantly, okay? But usually in the real world setting, right, you're not dealing with a lot of clusters, right? So naturally, you'll probably be able to work with just a few kind of underlying like hidden models, okay? So that usually would works like reasonably well, okay? But just know that it is challenging if you somehow underlying your problem setting, you are expecting many hidden like categories, or you just don't have enough data to work with, because you need all the observations for you to learn those models, right? So that's just generally challenging if your problem is complicated to start with. You're dealing with a lot of hidden clusters, or you just don't have enough data. That's hard, because to train the models, right, you need sufficient information. All right, okay, so we talk about probabilistic model, okay? Next one, high dimensional data. So we have mentioned, right, high dimensional data actually quite a bit. So we already said, give you a rule of thumb, right? If you're only dealing with a few dimensions, typically you're fine, okay? People have found that if you're working with a clustering, like with numerical data, usually when you go above 15 dimensions, that's when it becomes almost infeasible, for you to actually have meaningful clusters, okay? But in the real world, right, we generally see high dimensional data, right? So I think I mentioned we were working with the new materials, right? Those new materials, they have 40 plus descriptors, like attributes, okay? Or we were working with a gene expression data, right? That's thousands of genes as your dimension, right? If you're talking about documents, if you have keywords, thousands or tens of thousands, right? So you're naturally working with high dimensional data in many different settings, okay? What do, right? Because in this case, you would still like to have this high dimensional data, but still be able to find some clusters, okay? So that it will give you insights, right, regarding maybe potentially grouping or some categories you can work with, okay? So to work with high dimensional data, naturally you're talking about, okay, how can I reduce the complexity, right? We have already mentioned dimensionality reduction, right? There are quite a few methods, right? So starting with, say, a higher dimension, you can work with different approaches for you to reduce that to smaller dimensions. And once you have smaller number of dimensions, then you can use the more traditional clustering methods that are effective for lower dimension data, right? Another one is called a subspace clustering, okay? So the high-level idea with the subspace clustering is that I don't need to do the clustering in the whole space, okay? Or it's too hard to do it in the whole space, right? Rather, I'm trying to find a cluster that they're similar in certain dimensions, but not other dimensions, okay? So we'll talk a little bit more about that approach, okay? But at a high level, right, the thing is that when you have many dimensions, not all the dimensions are equal, right? Some dimensions are just not very helpful, or they're actually creating more noise or confusion, right? So you want to be able to maybe either identify those dimensions and remove them, or only select dimensions that are informative, right? Okay, so that's the starting point, right? Not all the information is useful, right? So you only pick the ones that are more useful. Okay, and also when you have a lot of dimensions, this also things that the distance measure becomes dominated by noise, right? Because if you say if I'm looking at my whole class, right? If I just ask about your major, I ask about which degree program you're in, or where you come from, I can probably have some good clusters, right? But if I start adding more and more dimensions, right? So because every dimension you add, those points, objects will be pulled in different ways, right? So the more dimensions that you use, right, there'll be more fuzziness or more ways to pull your data points in different directions, okay? As a result, right, you don't have those clusters, right? You may have a nice cluster in the 1 dimension or 2 dimension, and then when you add more the other things, they become spread out, and they don't form a cluster anymore, okay? And the main thing is that a cluster may exist only in some subspace, okay? So just intuitively think about it, right? If I'm trying to find like experts, right, in certain like scientific domains, right, I only need information about those domains, right? Maybe their research papers, the publications, right, where they get the degree or something, right? That may be sufficient. I don't need to ask about, oh, what kind of movies do you like, or what kind of things you have purchased on Amazon, where you have traveled to. Some of those may be relevant, but some may not, right? So the high-level thing is that, hey, your clusters may be more informative or more meaningful if you only look at a subset of those dimensions, okay? Now, there's a general notion, right, referred to as the curse of dimensionality. High-level thing just like, yeah, it gets harder when you have higher dimensions, right? So we say that basically you think about, right, if you have n data points, let's say 1 million data points, okay? You only have one dimensions. Of course, they are packed, right? As you add the dimensions, they become more spread out. Great, right? You want to spread things out to some extent so that you can find those clusters, but not to the point that when you have two dimensions, too many dimensions, and the things are all spread out. Now you're looking at a vast space with a lot of sparse data points. Because when you get to that point, right, your neighbors, right? So that basically the idea is that when you, in this case, right, so the points will be further apart from each other. As a result, your distance measure becomes meaningless, right? Think about it, right? In this huge sparse space, okay, the points are pulled in many different directions, right? So when you say, I'm trying to find my nearest neighbor versus my furthest data point, they don't differ that much because they differ some way, right? You tend to see that they are all actually kind of farther out, right? So the notion of like clustering, meaning that you're close to certain data points. You have a dense neighborhood, right? Everybody else is further out. It's not like it's no longer there because everybody seems similarly far away, right? So that's what we call equidistance. That means like you don't have a clear separation of your near neighbors versus further like objects. So let's say how the subspace works, right? We already said, okay, I don't want all the dimensions, right? And the cluster may not be meaningful in all the dimensions, right? Rather, I just need subclusters, right? Subspace, certain dimensions to help me to find the clusters, okay? So as our illustration showing here, with colors, it's much easier to see, right? But naturally, that's what I'm looking for, right? So I have like 3 dimensions, right? A, B, C, okay? And I have some data points, right? So in this case, right, you just look at the color, you actually see some natural clusters, okay? But to find them is actually not easy, right? Because if you project different ways, right? So for example, if I take dimension A, if I only look at dimension A, you will see that like I have, this is my projection here, okay? So you will see that there's like a bit of a kind of like a spike here and another spike here, but now the red is being combined with the blue and the purple. Green is also combined with blue and the purple, even though there's separation, but those points are not something you can see, right? If you try another dimension, right, here, for example, naturally now you see kind of the blue and the purple being combined in one cluster, and the red and the green now has become another cluster. Okay, so you can see basically when you play with your dimensions, right, you project it along different dimensions. You tend to see either individual cluster or a combination of maybe a subset, right, of your clusters. Okay, so let's look at like this example, right? Now maybe A and B and C individually, I see some separation, but they're still combined, right? Combined different colors. This is actually where you actually see a clear separation, right? Because now I have A and B, so I have 2 dimensions, right? In this case, the blue and the purple are still combined, which is not good, right? I cannot separate them yet. But I now have a very nice way of separating the red and the green, right? They're natural clusters which I can already pull out by looking at like A and B, okay? Or you can actually try other dimension. Now you can also nicely pull out the blue and the purple. Great, okay? So the high-level thing to capture is that when you're playing with your dimensions, when you look at the subsets of your dimensions, right, you can find certain clusters, not all the clusters, right? Usually it's hard to find all the clusters like in one projection. But by looking at your dimensions and the points from different perspectives, you can find different clusters. Okay? So if you talk about the recommender systems, right? Recommender systems is actually trying to find objects and users with similar interests, right? But it's very hard to find a global similar interest, like this group of people, like they all like all those things. No, right? We may be similar when we talk about what kind of like books we read, right? We may be similar, say, in terms of what kind of food we like, okay? So you will be similar, right? So you can say you will find clusters that are like actually inherently similar along certain dimensions, but not the other. So you want to actually ask this in many different ways. Okay, so that's a high-level idea, right? With that, we actually show that it actually can work pretty well, okay? It's not synchronized with my screen. Okay, very strange. Okay, so there's some different approaches, okay? But basically, the high-level thing is that you play with the different subdimensions, okay? Subsets of the dimensions, okay? Click is actually, we mentioned it earlier, right? That's kind of the, it's basically growing, right? Growing the dimensions, okay? But it's using the, basically dividing up the space, but also using density, right? To identify the dimensions and the space, the subspace that is actually the grid cells, right? That can be potentially a cluster. Okay, there are also other methods which will not get into frequent pattern. Remember, we're using like pattern-based mining, right, for classification. Similarly, if you have identified some frequent patterns, right, knowing those are the things that are occurring together, that is actually naturally a subset, right, of dimensions you may work with. For example, like if you look at our purchase records, right? So you say we tend to, like, say certain customers tend to purchase certain things together, right? And that frequent pattern by itself may be able to help us to identify clusters of users or clusters of objects, right? That means some natural grouping. All right, by clustering. So here the idea is that when you have like clustering, already said, right? We may not be able to find clusters along all the dimensions, okay? So by clustering is actually saying that, okay, I'm trying to group both the dimensions and the attributes. The dimensions and the objects. So that means my goal is not to group everybody, because earlier with subspace clustering, right, you still, even though you're choosing a subset of the attributes, but you're still trying to cluster everybody, okay? Well, the by clustering says that I'm not trying to find it like everybody, like not everybody need to belong to a cluster, okay? So one scenario that is one application, so we were working with this gene expression data. So that the idea is that you look at the gene sequence, right? And you're trying to look for like genes like that are similar or they have similar function or similar expression under certain scenarios, okay? So in that case, right, I'm looking at subsets of the genes. And also, I don't care whether they are similar across all the different dimensions, right? So this is where like scientists do all kinds of experiments, right? The heat shock, they put them into cold temperature, they put into some kind of a solution to see whether things are more expressed or not, okay? So the idea is that to find those clusters, right? I'm looking for genes, like a subset of those genes. They are similar along a subset of those scenarios. So I don't care about the other things, right? So if you like visualize this, right, what we're trying to do, right, we're basically trying to like take the clusters and somehow they become similar only along here. So that means a small kind of like a subset, both from the horizontal dimension. Horizontal means that the different objects, and the vertical is only a subset of the attributes. Okay. So here we have an example, right? If you look at all this, right? So this is the different objects, and they have like their response somehow expression under different scenarios, right? If you look at all this, you don't really have a way of kind of finding similarity, right, or grouping them. But if you only select, right, a subset, so that means instead of all the different scenarios, right, I only select a few, and now I actually have this very natural pattern, right? They're all similar along those dimensions, like ABC, right? If you only look at them, and you only look at those dimensions, wow, this is actually very good, like similarity. Others, I don't care, right? But also knowing that the similarity can be defined differently. Like here is more like a relative, this all same scale. This is a different scale, but it gives you also a similar trend, like going up or down depending on the different scenarios. So you can define your distance function differently, but the high level thing with bi-clustering is that I only care about a subset of the dimensions, and I only care about a subset of the objects. I don't care about the other ones, okay? All right, graphs and networks, okay? So we talk about classification, right, with graph and networks. Now with clustering, similarly, right, you are trying to find things that are similar, okay? I'm not necessarily classifying into different categories, but I want to find things that look similar, okay? So apparently here you need a way of finding or defining similarity, okay? So to work with this kind of thing, you basically have different approaches, right? Of course, starting point is that what kind of graphs you have. But with that, right, when you're trying to cluster your graphs, okay, either you have this generic method, right? So that means I just need to define, right, the similarity or distance between those data points, right? Once you have that, then you have a way of finding which ones are more similar, okay? Or you can have some like graph-specific method, okay? I think I have a couple examples here. So this is again a density base, right? This is actually what we kind of mentioned earlier, like with the communion, right? The idea is that I'm basically defining those neighborhoods, right? I'm using the cut to identify ones that are not as closely connected, okay? So with the graph clustering, right, generally you have this notion of like structure connected components. That means they are well connected, right? So here visually you can see I have this purple graph, and then we have this kind of more of the beige or like a light orange color, right? So one of those, like if you're kind of in this big neighborhood, right, that's like, okay, I'm kind of densely connected to everybody. Great, that's a nicely connected like sub-community. But then you also have this what we call hubs, okay? So you can actually imagine like what do you mean by hubs? So hubs are people who can connect between communities, right? So for example, like I'm working with electrified transportation, right? So I'm actually connected to this community, but I also work on data mining, right? So I may be the hub point, right? I can actually bridge different communities, okay? And each of us are probably doing something like that, right? You have different communities that we belong to, but we also act as the bridge or the hub between those. And of course, with that, you also can identify outliers, because outliers are just they don't belong to any bigger community, so that means they are kind of dangling, right, like around in the bigger graph, okay? So many of those actually graph visualization is actually very helpful, right? If you're like playing with the graphs, that may be something you want to try anyway, okay? So you can visually actually identify some kind of dense clusters in the big graph, right? But also there are specific ways for you to actually calculate, right, the connectedness or like the weighted, right, ties between different components of your graph. Okay, well, almost done. I want to just finish the discussion with clusters, okay? So semi-supervised, this is again the scenario where say you don't have to just do things blindly, right? They're basically constraints we can leverage, right? So sometimes it's like only consider objects with certain properties, right? You can do that constraint on the object level. You can also select like certain parameters that we have talked about, right? Or you can do constraint on what kind of function you use, right? Do you consider weights? Do you consider obstacles? So I'm going to show, I think I have an example after this, okay? So the user maybe will say, okay, I only care about classes with certain properties, right? They can actually tell you that, okay, don't worry about other clusters, right? Focus on those clusters with those kind of properties, okay? And sometimes this like semi-supervised says like, okay, I don't know the global clustering saying, but I have knowledge that those points should be together, or I have knowledge that those points cannot be together. They're not in the same category, okay? Those are the kind of information we can all leverage, right, when you're trying to build up your clusters, okay? Here is an example. This is about clustering using obstacles, okay? So in this figure, this is like physical space. I think the application scenario is about like if you want to set up a new kind of ATM machine, right? So you want to make sure it's close to your customers, okay? So if you don't consider the physical structure, you just look at the ground distance, right? If everybody is going straight, right, you would have those clusters, meaning that, okay, given where my customers are, those are the data points, right? These would be the places I would place my ATM, okay? But turns out, right, in the physical space, you actually have all those obstacles. That means like those are river, there's buildings, so your customer cannot cross the river anywhere. They have to go over a bridge, right? Or if there's like a building, they cannot really kind of easily just go through, right? So if you want to take all that information, so basically you're playing with your distance function, right? This actually is the new result, okay? By leveraging that real-world property so that you can generate clusters that are more meaningful. So in this case, you can see, right, now you have different results, and now you're actually avoiding, or actually you're counting the detour that your customers have to take, right, when they go through the different, when they have different obstacles, okay? So that actually ends our discussion. I think we're out of time, so we'll stop here, okay? Quick reminder, homework 5 is due this Thursday. And if you haven't finished your survey and you need a special accommodation for the midterm exam, please contact us as soon as possible. All right, that's all for today.